Find target 5. We're using the property of arcs and chords in this one. All right, and so our big question is, how are you going to use properties of triangles and circles to come up with the properties of the arcs and the chord, okay? So our vocab for this one, 360 degrees. Arcs, everybody know what an arc is?
Yep.
Good. Bisects, everybody know what that means?
Yep.
Awesome. Central angle, everybody remember what central angle is?
I understand.
Awesome. Congruent. Converse we haven't really talked about as much. The converse is the flip. So if I say it's raining outside, the converse is it's not raining outside. Okay? We know what equal is, we know what perpendicular is, and once again we're going to use the Pythagorean theorem. So, okay, what we're going to do is we're going to look at some triangles that are created by congruent central angles in a circle. Okay? So, what are my congruent central angles in this example right here? Huh? Oh, I think we're going to have to get the cards out. Okay, Kaylee Yamas. What are my two congruent central angles? But how do we, what are the names of them? Angle EAD and BAC. Okay, I agree. Perfect. Okay. All right. So since all the radius of the circle or radii of the circle are congruent, okay, that means this side's congruent to that side. Would you agree with that? And that side's congruent to that side because they're all radius. And all radius have to be the exact same size. All right? So if I then connect the points here to here, what property or theorem can you say that triangle ADE is congruent to ACB? What? Go back to our triangle congruencies.
Is it side, side, side?
Do we know three sides?
Well, we have
Side
two.
angle side.
We have two sides in the included angle, so we can say that the angle or side angle side congruency theorem. Perfect. Okay, now go back in your memory banks. Since this triangle is congruent to that triangle, how can we say BC is congruent to DE? There was a theorem. It has an acronym.
CPC.
Yep, that's it. Corresponding parts, because this part corresponds to that part, of congruent triangles are congruent. Good job. Good job. Okay, so the conclusion that we can make is that if we have triangles created by congruent central angles, then the chords created by those triangles are always congruent. Okay? And the converse is also going to be true. Congruent chords have congruent central angles. Okay? And this means that our arcs are also congruent because our central angle and our arc are equal. So I think that's where everybody is for the most part on that one. Okay? Okay, so let's calculate DE. All right? We're looking for this part right here. BC, so this one here is equal to 3z minus 6, and DE is equal to 2z plus 6. Okay? How can I solve for z to find out what the length of DE is? Say that one more time, Brooklyn.
2z plus 6 equals 3z minus 6.
Is equal to 3z minus 6. Why are you saying them equal to each other? I agree, but why? How do you know this one is equal to that one?
Because they were saying that.
Yeah, but you're setting them equal to each other. So how did we know that this side length was equal to this side length?
Is this the same triangle from the beginning?
Mm-hmm.
Very different size.
Because we proved that the triangles are congruent, so that means these two are congruent. Okay, awesome. All right, so if I solve for z, that means that z is equal to 12. Do you agree with that? And so if I'm finding DE, that means that 2 times 12 plus 6. So DE is equal to 30. Are we good on that one? Easy peasy? Alrighty. So, arc measures. The measure of a minor arc is equal to the measure of its central angle. Okay, that was we did that one in, I think, what, 3 or maybe? And remember, all central angles sum to how many degrees? 300 and what? 360. Perfect. Okay? So let's find the following measures. So I'm looking for CE. What's the measure of that going to be? Do I have a central angle here?
You have this.
And the arc minor is, the minor arc is equal to the central angle. So since this is 56, that one's going to be 56. Okay. BF is here. What do we know about this angle? They're vertical angles, which means this angle is going to be 56, which means my arc's going to be 56. All right, let's look at DE. My arc's going to be 90. Perfect. Then we're looking at DB.
90.
Right, so if I look at my semicircle, I'm going to have 190 minus 90 minus 56, which leaves me with 44. Oh, I'm sorry, 180. What am I thinking?
Yes.
Good Lord. Not awake. So what's that equal to? 34. Durr.
Does that mean the angles inside are equal to 34 or like 56? Does that mean that those angles are equal to the arc?
So that means this angle is 34.
Yeah.
Jacob.
So is this just like writing 33 then?
It's a continuation of it. Yeah. Okay, there's more, I'm just kind of reviewing this part before we go into more of it. Okay? All right, so that makes CF going to be equal to what?
Changes.
How about 180 minus 56? Because I could do a semicircle here, or I could do a semicircle here, either way. Or I could say these two combined are going to give me a vertical angle, but we'll just look at it this way. And so it's going to be 124, which makes my arc length 124. Okay. Alrighty. Alright, so first question. What type of triangle is created by the radii AB and AC? If I connect B to C. What type of triangle is that? Mr. Rupp. What type of triangle is created? Yep. Perfect. An isosceles. Okay. The radius AD, okay, is perpendicular to chord BC. So how could we show that triangle ABE is congruent to ACE? Think about what we know. If this is perpendicular, then those two are like that, right? We know this is equal to this. What else do we know?
There's an angle.
Do we know any more about angles? But what about AE? No, I was thinking about the segment AE. Is that congruent to each other? Okay, so there is a theorem that says if you have a right triangle and your leg and they call it hinge, but they mean the hypothesis. If they're congruent, then the triangles are congruent. Because remember, thinking back to our congruent triangles, this would have given us SSA, right? Or ASS, and that's not a good one. If it's a right triangle and your leg and hypothesis are, then that is valid. Okay? So, if these two are, this triangle is congruent to this triangle, then I can say that BE is congruent to EC by what theorem? Say it fast, 5 times. CPC-TC, I can't say it. CPC-TC. That's all right. All right, so how can you show now, why do we now know that EAB is going to be congruent to that one by the same thing? Because all congruent parts are congruent, okay? And so what does that imply about my arcs? If this angle is congruent to that angle, what does that tell me about these arcs? It means my arcs are going to be congruent, right? And so my conclusion is, if I have a radius and it's perpendicular to my chord, then it bisects the chord and the arc. All right? That's a big theorem. So, if I have okay, and I guess let's talk about this for a minute too. Because you have the chord and the radius creating that right triangle, you can also use your Pythagorean theorem. Okay? So, if CD is 72 and AC is 65, I want to calculate the whole thing, DE. Okay? What's DE going to equal?
There's 180 bisecting.
Because if we drew our triangles, we would have congruent triangles, which would make this one congruent to that one. And so DE is going to be equal to 2 of these. And so DE is equal to 2 times 72, or 144. Okay? And so if I want to find AB, what could I do? Actually, I want AC. No, I have AC. Oh, I'm sorry. No. I'm thinking backwards. AB. If I can find the length of AD, okay, so AD squared is going to equal 65 squared plus 72 squared. Okay, so if I calculate that out, it's going to be, squared. I already did this. Plus 425. So AD squared is going to equal 9409. How do I find what AD is? Take my square root. And so AD is equal to 79. Okay, good. Questions? Big theorem is about the central angle and arc, revisiting that and knowing that it's perpendicular and it bisects your chord. And then using what you know about all of the congruent triangles to be able to solve for the different parts.